Heat engines are devices that allow us to use thermal energy to actually get some work done. And the idea of a heat engine is you can start with something at a high temperature, high heat, and you can allow that heat to flow to a lower temperature reservoir, lower heat, and as that's happening, you pull some of the energy out and you get it to do work. And that leads us to the idea that QH is equal to the work plus QL, because energy is conserved. And so we can look at this and we can say, all right, we've got to start with high heat, high temperature, and with low temperature. And the reason for that, if you think about it, it's easy to think about this in, say, a steam turbine. You have a tank of water over here, and you put heat underneath it. That steam is captured, and it goes through a pipe, and then it feeds into a turbine, which is essentially like a propeller. And it causes these blades to spin, and then this exhaust steam is allowed to flow back into a condenser and then pumped back into here. Okay? And so why do we need a temperature difference? Well, if this is hot and this is hot, then the pressure here and the pressure here are the same, and that means this thing isn't really going to rotate. But if this is hot and this is cold, then the higher pressures here, that's going to allow this to turn, and then we can collect our exhaust and redo the process. Okay? So this is our high heat reservoir. This is where we're putting in energy. We're making everything, lots of internal energy here, and then this is, we'd have a tank over here to collect that, and we'd have to pump this back into this reservoir. And so we have our low heat reservoir. And the difference between those two is the work done. And what we think of is we can say, well, how well does this engine do work? And we think of that in terms of efficiency. And efficiency is how much work you get out of it compared to how much energy it takes to maintain this high heat reservoir. So we have that. This only works, this equation for calculating efficiency tells us if we know how much work is done, but there's another way we can actually think about this. If we come back up to this equation, we solve it for work, we see that work is actually equal to the difference between the two energy reservoirs. So if we come over to this and make that substitution, we have QH minus QL divided by QH equals efficiency, which is really just 1 minus QL over QH. And so this doesn't depend on how much work was done at all. We can figure out the efficiency of our engine, our heat engine, just by looking at the differences in the temperatures of the exhaust side to the thermal side, to the high energy side. Now, a bunch of work was done, and it can be shown that when your working fluid is a gas, working fluid is the thing that actually carries the heat from the high to low process or high to low reservoirs and does the work, that the efficiency actually, or the heat in each reservoir is directly proportional to the temperature in each reservoir. And so the ideal efficiency of an engine, and now you got to think about this. We're talking about an ideal gas, no friction, no turbulence, no energy is ever wasted on opening or closing valves or pumping water back into a high heat area. The only thing we get out of this ideal is completely reversible processes, no energy wasted, is that really we could say the efficiency is 1 minus the temperature of the high heat reservoir divided by the temperature of the low heat reservoir instead of the heat that's moving around. And temperature is much easier to measure, so this is very, very handy. So the ideal efficiency of a heat engine is given by this. Now temperature does have to be, oh sorry, not high over low, low over high. Temperature does have to be given in kelvins. Okay? T in kelvins, because the energy is proportional to its Kelvin temperature, not Celsius or Fahrenheit temperatures. Okay? So if you think about this, this equation sort of tells us right away that you're never going to have a 100% efficient engine unless you can get down to absolute zero. Okay? So for normal everyday operating temperatures, you're not going to have an ideal 100% efficient engine. But the lower you can make that low energy reservoir and the warmer you can make the high energy reservoir, you have the potential for increasing the efficiency of your engine. Now, related to heat engines are refrigeration cycles. Now if we come back up to this, we can see that if you let heat flow and it spontaneously flows from hot to cold. In fact, that's the second law of thermodynamics. Okay. Second law of thermodynamics And there's a bunch of different statements of this law, and we're going to look at another one. But the second law of thermodynamics says heat flows hot to cold. Okay. Now this is a pretty specific instance of this law, but essentially it's saying heat doesn't flow cold to hot, at least not spontaneously. Okay? And it comes back to the idea of this law, or high temperature equals work plus low temperature reservoir. Well, you should be able then to say, let me draw that diagram again, QH is here, QL is here. If we were able to get some work out as this flowed naturally this way, we should be able to put some work in and get heat to move against that pressure or that temperature gradient. And that's the idea of a refrigeration cycle or a refrigerator. We're trying to get heat to move backwards. Use work to make heat flow cold to hot. Okay. So a heat pump moves heat around. Refrigerators, air conditioners, they're moving heat from an area that's generally cold to an area that's generally warm. And they work in a pretty simple fashion. Essentially what you have is a unit that's able to do work, and it's a pump. Okay, it's a compressor pump, and it's hooked up to a condenser series of pipes. Condense means to change from a gas to a liquid. Okay, and this is on the outside of whatever you're trying to keep cold. And then these pipes are connected through a valve to another series of pipes, tubing, and this is what carries our working fluid, our refrigerant, the fluid that can transfer the heat around. And so this valve, it controls how much fluid can move in here. And so this over here is on the inside. So there's a fluid that we are able to manipulate and do some work to in order to get energy to flow one way or another. So what we do here is this pump actually compresses the gas, right? It does work on the gas. It decreases, well, it doesn't decrease the volume, but it increases the pressure in here. And when it does that, it forces this refrigerant into the liquid phase. Okay. And so that means it's going to be very hot over here. These particles are going to have lots of internal energy, and so heat is going to naturally flow on the outside of this refrigeration unit from the high temperature in the pipes to the relatively cooler temperature outside. So heat flows out of the tubes, and so this liquid as it comes through here, well, this vapor I suppose, as it comes through here is able to condense down into a liquid state because this pump did work to increase its internal energy, and so this heat flows out. Now, it works through this valve very, very slowly. This expansion valve only allows a small volume of gas or liquid through, and so we get very, very low pressure over here. And so that means that the internal energy is going to be less. This is allowed to expand through these pipes, and as it does that, it can change from a liquid phase into a gas phase, and to do that, it has to absorb energy from the surroundings. So even though this side is relatively cooler, because we lowered the pressure over here, we can allow this gas to expand and absorb energy from its surroundings. Then it takes in the heat from its surroundings, and then the pump pulls that back through and shoves it to the other side. So this pump is actually doing the work to move this fluid from low pressure to high pressure, and that allows us to move heat from cool to hot. And so we're able to keep this side cold and expel the heat that was in this side to this side. And again, this is never going to be 100% efficient. You have to, the pump is going to have to do a little bit more work than you actually move the heat, but it is a very useful modern invention that helps us basically have the lives that we have. So heat engines and refrigeration cycles are both important in thermodynamics. They both allow us to manipulate heat using work.